Good evening, everyone, and welcome to the final lecture for this evening. We've got a question to start off with. In our context of gradient descent, the gradient is not normalized. So, I mean, I suppose we're talking about. I'm guessing we're talking about question 3 on assignment 3 there. And just looking at the equation that you're given the equation x of t plus 1 equals x of t minus eta times the gradient of L applied to x of t. And so, strictly speaking, that's not normalized. I guess eta, when you normalize gradient descent, essentially what you're doing is either slowing it down or speeding it up according to what you feel like doing. It looks like in this context, in the context of the assignment, eta is the thing that you're using to control the speed. So you can think of that in a sense as a normalization, although it's not normalized so that we're only going in the direction with one unit speed, but nevertheless it is some normalization. But to answer your question, I suppose I'd say it's not normalized according to the definition of normalization that we've been working with. Yeah, so you're right. So yeah, eta is just, as you suggest, eta is just a value that you play with, and so you get convergence. I mean, strictly speaking, you would need eta to be small enough in order to expect convergence of your gradient descent algorithm. You may have found that if you make eta too large, then you're not likely to get, well, it's harder to obtain good convergence results in that sense. Does that answer your question? Another request to explain question 1F. So show this empirically, I suppose, just means just generates 10 to the 6 random numbers, plug them into the distribution that you're dealing with, and hopefully you'll get the same sort of probability that you've been told should occur analytically a bit earlier in the question. I probably don't have time to go too far into that in great detail now, but yes, I'll probably make a start with the rest of the class content now. Okay, so this evening I expect that this evening's lecture will take about 2 hours. I'm actually only going to take the first of these hours, and then after that, Yoni will be taking the second hour, and he'll be talking about gradient descent and neural networks, I believe. And so this hour is actually the last time I'll have with you. And the content that we'll be going through this evening is the normal distribution. So we got close to actually talking about the normal distribution when I spoke to you a couple of weeks ago about probability theory. And we talked about random variables, and we talked about the different ways these random variables can be distributed. But there was one very important one that we didn't actually go through, and this is the normal distribution. So let's talk about that. So remember, probability theory, we are primarily concerned with these things called random variables. So in this context, we've got x. So x in this context is a random variable. Now, as we discussed, we talked about probability density functions for random variables. Now, definition, we say that the random variable x is normally distributed, or we say it has a Gaussian distribution, if it has a probability density function, and if the probability density function looks like this for some real parameters mu and sigma squared. I guess strictly speaking, we need sigma squared to be positive. So this is the probability density function. So this parameter mu, roughly speaking, tells us where the probability density function is centered, and sigma squared describes how spread out this random variable is. So we can see this quite precisely with this box down here, properties of the Gaussian distribution. It is precisely true that this mu parameter is the center of the random variable because the expected value of this random variable is mu. On the other hand, the variance of this random variable is sigma squared. So you may recall, maybe you recall, maybe you don't, that the definition of the expected value of a random variable, to work this out, you need to integrate not just the probability density function, but the probability density function multiplied by x dx. And if we call this mu, then the variance of x is defined to be the integral of the probability density function multiplied by x shifted by mu squared, f of x dx. So this is how we defined the expected value and the variance. And it turns out that for the normal distribution, the two parameters mu and sigma squared, which you have to specify in order to uniquely determine your random variable, mu is the expected value and the variance is sigma squared. And so here you've got a picture which I think describes quite nicely the role of these particular parameters. So we've got this first one here, which is centered in the middle. For this one, the expected value is 0. And the variance, which is sigma squared, is equal to 0.5. So remember, mu basically tells us where it's centered, and sigma squared tells us how much it's spread out. So if we look at this one now, the normal distribution with mu equals 0 and sigma squared equals 1, well, it's still centered. It's still centered at 0, but because the variance is larger, we can see that this function is much more spread out. On the other hand, if we look at the normal distribution with parameters mu equals 2 and sigma squared equals 1, the variance is the same as this one, but it's centered at a different location. So that means that, you know, the rough structure of these two peaks are the same. It's just that one is centered at mu equals 2, whereas the other is centered at mu equals 0. So this is the bread and butter of a probabilist's theory, because this is the essential distribution that everyone should know about. And we really should have done it a couple of weeks ago when I was talking about probability theory. Didn't get a chance to, but that's okay. We can talk about it now. So it's essential that we understand this probability distribution because it comes up all the time. Now, to start our dive into this particular distribution, we have to actually show that it is a probability distribution. What do I mean by that? Well, the one thing that we need a probability density function to have, and the one thing we haven't checked yet, although I understand you had to do this in your assignment, was to check that this probability density function integrates to 1. Now, yes, I'm aware that this is essentially a question that you had to do / are currently doing for your homework assignment, but Yoni tells me it's okay for me to actually go through this particular question in great detail. So let's get on with it. So really, in order to check that this function is a probability density function, we need to check that it's continuous and positive. Well, I mean, we're taking the exponential of a continuous function, so that's always positive and it's always continuous. So we don't really need to worry about those two. However, what we do need to worry about is checking that this thing actually integrates to 1. So how do we do that? Well, just integrate this from minus infinity up to infinity and see what pops out. The first step is actually one of convenience. It turns out to be quite convenient to change variables before you go plowing through this integral. So since we're taking the square of this somewhat ugly thing here, I'm going to let that thing be a new variable. I'm going to say let u equal x minus mu divided by sigma. I'm integrating with respect to x, so I need to know what the derivative of this guy is with respect to x. That turns out to just be 1 on sigma. So that means I now have enough information to rewrite my integral. So I take the integral I was originally dealing with, I replace this with u, but I replace the dx with dx replaced with du on sigma. Oh wait, did I do that right? No. Sigma goes up the top. And so this is why this sigma cancels out here. This is why it's nowhere to be seen up here. And so you might say, well, this was pretty silly because I didn't know how to do this integral, and I don't know how to do this integral either. So what have I actually achieved here? So the answer to this really is I haven't really achieved much. I've just made the integral look a bit nicer. In particular, why would I say this integral is nicer? Well, in this integral, we had mu and sigma, which were unknown parameters lying around. But I've shown that this integral is 1 is the same as showing that this integral is 1. And this has no dependence on mu and sigma. And in fact, it's precisely the probability density function you get if you're looking at a normally distributed random variable with expected value 0 and variance equal to 1. So really, what I'm pointing out here is that to show that this integrates to 1, it suffices to show that it integrates to 1 in the special case that mu equals 0 and sigma equals 1. So really, all I need to do is show that this integral, I just need to show that this integral is 1. So this is the first step. As I said, we haven't really achieved much so far, but we have somewhat simplified the problem. Okay, now we know that this is the thing we're trying to do. So how do we do that? Well, this is just me copying the result from the previous slide. Remember, all we're trying to do now to show this proof, it suffices to show that this thing integrates to 1. Now, this is where things get really interesting because it's really hard to show that this integral is 1, at least just with the theory of integration. Single variable integration, that is. What is so remarkable about this integral is that the simplest way to do it is to actually pass to multivariate integrals instead. It's one of these bizarre things in mathematics where in order to solve it, you really have to go outside of the paradigm that you're currently working in. So as I said, what we're trying to do is integrate this using multivariable integrals, the volume integrals that we've already dealt with. So how does this go down? Well, let's just, before we introduce the multivariate integrals, note that showing that this integrates to 1 is the same as showing that if you just integrate e to the minus x squared on 2 and square that result, then you get precisely 2 pi. So if you take the square of this equation and rearrange, you're going to end up with this. Okay, how do I do that? Well, this is where the trick really comes in. You say, well, if I'm integrating something and then I'm squaring that result, that's the same as doing that integral and then multiplying it by that same integral again. So integral e to the minus x squared on 2 dx, integral of e to the minus y squared on 2 dy. Now, I guess originally when we wrote this, we would have written this as e to the minus x squared on 2 dx. But as I've tried to convince you on a number of occasions this semester, this x, if you've got an x inside an integral that you're integrating with respect to dx, then that's just a dummy variable. You can replace it with any other number, in particular, sorry, any other letter, and let's, for argument's sake, choose y to be our letter. Now, there are no parameters in here. The integral from minus infinity up to infinity of e to the minus y squared on 2 dy, this is just some real number. It's a constant. So that means I can actually put this constant inside the other integral. So now I've got integral from minus infinity up to infinity of e to the minus x squared on 2 times that same constant we were just dealing with, the integral from minus infinity up to infinity of e to the minus y squared on 2 dy. But we now recognize that this is precisely the volume integral over all of R2 of this function here, e to the minus x squared plus y squared divided by 2. Okay, so we've converted the problem into showing that this particular double integral here evaluates to 2 pi. So we want to show that this integral is equal to 2 pi. Okay, how do we do that? Well, you may suggest that this integral here is actually even harder than the one we started off with. So why would introducing volume integrals be so helpful here? Well, the answer to that is that in 2 dimensions we have access to polar coordinates, and since we have access to polar coordinates, that actually makes this integral a bit easier. So how does this work out? So remember how we convert to polar coordinates? We have to go r squared equals x squared plus y squared. And remember, dy dx is not just equal to dr d theta, but it's equal to r times dr d theta. So I've tried to help you remember that by putting this r in bold there. And this is really the thing that allows us to do this integral, because this opens this integral up by this opens up the possibility of using integration by substitution to do these integrals. So this equality here is basically all I'm doing. All I'm doing here is passing from Cartesian coordinates to polar coordinates. So r travels from 0 to infinity, and theta travels from 0 to 2 pi. Okay, how do I do that integral? Well, the inside integral that we're dealing with, we've got this outside 0 to 2 pi integral, but on the inside, what we've got is this integral here, the integral of e to the minus typo. I myself have forgotten about the thing I kept telling you to not forget. We need an r here. So the integral from 0 up to infinity of r times e to the minus r squared on 2. And the way you do that integral is with integration by substitution. So you would go u equals r squared, so that's du on dr is equal to 2r. And then what we find is that that this integral becomes the integral from 0 up to infinity of e to the minus u divided by 2 r times dr. Well, we know that r times dr is equal to du divided by 2. So this is the computation that you need to do that will allow you to actually evaluate this integral. So as I said before, it's this inclusion of this factor of r here that allows us to work this out explicitly. And we only got that because we passed to polar coordinates. So this is the reason that introducing the double integral was necessary for this particular computation. Okay, so as I said, this integrates to 1, but if this integrates to 1, then the integral from 0 up to 2 pi of 1 is just 2 pi, But remember, this is exactly the result we were after in the first place. We wanted to show that this double integral was equal to 2 pi, because that implies that the integral from minus infinity up to infinity of e to the minus x squared on 2 dx is equal to root 2 pi, I think. So this is the result we were after. And yes, this is an essential computation. This is quite interesting because this is an essential computation that all probabilists need before they can start working on the normal distribution. But it's something that you can't actually work with until you know how to do volume integrals. So I guess it's one of these really unfair situations in which you need to know rather advanced mathematics before you can do even basic probability theory. Are there any questions about this computation? I'll just give a quick half-minute pause perhaps. Yes, that's an excellent question. So the question was, is there another way to get this result apart from this double integral approach? Could we perhaps use Taylor series or some other thing like that? I'm certain there would be other techniques to prove this particular result, but I think this might be one of the easiest ones. I might have to get back to you on that one. As I said, there might be easier ways of doing it, but I can't think of really clean ways of doing it off the top of my head. Any other questions? All right. Yes, I'm not convinced that using Taylor series will actually work. It maybe if you can come up with an argument and try and convince me, that could be something worth doing. All right. Anyway, this is the standard proof that you'll see everywhere. But yeah, I'll look forward to hearing if there are any other ways of doing it. All right. Now, another question that comes up in your assignment, I believe, that Yoni said he's happy for me to do for you, is this one here. We've now shown that the normal distribution, that the PDF we're claiming that the normal distribution has is actually a PDF. We've shown it's a probability density function because it integrates to 1. There were two other things I claimed, namely that if you've got the normal distribution with parameters mu and sigma squared, then mu is actually the expectation of this random variable. Now, we sort of got an intuitive idea about why that would be the case simply by looking at the graphs we saw before. We saw this, well, like the center is really at this point mu, but it's something we do actually have to prove. So let's try and prove that. Now remember, by definition, the expectation of a random variable is equal to x times this. And we want to show what this question is asking us to do is demonstrate this integral is equal to mu. So let's get on with that. So I'll just throw the entire computation at you, and we'll try and work this through line by line. So how does this work? Well, so this line here, as I said before, this is just the definition of the expectation. But now what comes next? Well, this second line, what I've done is made the substitution y is equal to x minus mu. Now, this is a somewhat trivial substitution to make because Well, in this case, we find that dy is the same as dx. So that means we're able to just replace dx with dy immediately. X minus y becomes y, and x becomes y plus mu. So as I said, they're basically just a really simple change of variables there. You'll see why I made this change of variables in a second. Well, actually, you'll see why right now. So we're going to use the linearity properties of this integral. So if we've got the integral of y plus mu, then that's the same as the integral of y plus the integral of mu. Of course, both of these terms have these things attached to it. So all I'm doing here is using linearity of the integral. Okay, now what's going on with this next line? Well, actually, there's a bit going on. If I'm going from this step to this step, what have I done? Well, this first integral has just become mu. Why is that? Well, we can take the mu at the front of this particular integral, but what we're left with is the integral of e to the minus y on sigma squared divided by sigma times root 2 pi. But remember, this thing here, this is a PDF. And we just showed that this thing was a PDF because it integrates to 1. So mu times something which integrates to 1 is of course going to also integrate to 1. So that's all I've done there. What about this next part? Well, what I've done here is I've split this integral up into 2 integrals. So here I'm just using the result that if you've got an integral, you can break it up as the sum of 2 integrals on a partition. So this is the only thing I've done there. But now I claim that this last line, when I go from here to here, I just get mu. My claim is that the sum of these 2 integrals is actually equal to 0. Now, I haven't explained why. So this might be a question for the audience, perhaps. Can you see why these 2 things would add to 0? Please put your answers in the chat if you can. Yes, very, very close. Yes, you got it wrong the first time, but you realized your mistake immediately. Yes, indeed. Odd functions always integrates to 0. And I thought I might quickly jump to Wolfram Alpha to show you why. So of course, Wolfram Alpha is the baby version of Mathematica. If we look at the function we were just dealing with, we were looking at y times, if we set sigma equals minus 1, for example, sorry, sigma equals 1, then we're trying to integrate this function here. But e to the minus y squared on 2 is an even function, whereas y is an odd function. And so the product of these 2 is going to be another odd function. But if we're looking at the integral, what are we actually doing? We're looking at the signed area underneath the curve. Everything that occurs on the right part of the y-axis has a positive sign, whereas anything on the left-hand side has a negative sign. And as you can see, these areas are essentially identical. And so they cancel out in the way we wanted, and we end up with this computation is going to mu as we wanted all along. Now, you might be unconvinced by that. You might say you shouldn't be allowed to just point to pictures to conclude that these things add to 0. And yes, you are certainly right. The key insight that is missing in order to show that these 2 things add to 0 is another integration by substitution. So for example, what you might do is you would take, for this particular integral, you might take y equals minus z, change your integral appropriately, and then you would see that these two things actually cancel out exactly. So this is how we do this particular computation. This is how we show that the expectation is mu. Now, there is another one, another claim I made that needs to be verified, and that was if you've got a normally distributed random variable with parameters mu and sigma squared, then the variance of x is exactly sigma squared. Now, this is actually, it's a bit of a step up from the sort of integrals we've been dealing with already. So I'm not going to actually go through all of the details. I'm just going to give you a rough sketch of what goes on, just to give you, hopefully to convince you that this result is true, that it's possible to prove, and to leave the really dedicated among you to verify this yourself. Okay, so remember, definition, that the variance of x is defined to be the integral from minus infinity up to infinity of the probability density function multiplied by x minus the expected value of x squared. But remember, we said already that the expected value of this distribution is just mu. So we've just got x minus mu there. And of course, this is precisely that integral there. All right, well, what goes on now? A few tricky steps. So the first is your usual substitution. I want to introduce a new variable so that the new resulting integral essentially doesn't depend on any parameters. So if I said u equals x minus mu on 2 sigma, then of course du on dx equals 1 on 2 sigma, and I end up with this particular integral there. Now, of course, there is still one parameter here, sigma squared divided by 2 root pi, but the thing I'm trying to integrate now doesn't have any dependence on parameters. The integral of u squared e to the minus u squared du. Now, I'll invite comments at this point, so please put a comment in the chat. What integral technique do you think I need to use to evaluate this integral here? Yes, we've got someone who suggests integration by parts. And yes, that is indeed true. It's a bit tricky because in order to really use integration by parts, you've got to somehow introduce and you've got to introduce an antiderivative for this function here. Now, it's simple enough to simply define an antiderivative for this function. In fact, it's something along the lines of the error function that you may have come across before. So you can do this integration by parts, but the simplest way of doing that is by introducing even more notation. You introduce a new function, the error function, which is the antiderivative of this e to the minus u squared thing, and you proceed that way. And in order to use integration by parts, you have to observe, you need to work out what the limit of the error function is as you take x to infinity and so on. So it's these considerations that I wanted to allude to without actually doing, because it is a bit complicated and requires introducing even more notation that I didn't particularly want to do tonight. So this is basically all of the theory behind the normal distribution that I wanted to go through with you tonight. Now I want to get to explaining to you give you a few reasons to convince you that this is actually a really important thing to study. Okay, now The first thing I wanted to point out to you is that even though the Gaussian distribution really has its roots in probability theory, it actually comes up a lot in physics. And the way to convince you about why that is true is to consider the following. Take the normal distribution, take the probability density function, set mu equals 0 just for argument's sake, but we're not going to set sigma squared as anything specific. Instead, we're going to define sigma squared as being time and think about what happens as we travel through time. So we start at time 0 and travel through increasing time, increasing sigma squared, and then see what happens. Well, we've got this great function here. I have to confess, I made a bit of a literary error here. I referenced this picture as being from a Stack Exchange post, but I now realize that actually the person who posted this just ripped it from a textbook. I don't know what that textbook is, but there is some textbook out there that has this nice picture here. So semantics aside, let's talk about this picture. So as you can see, each given probability distribution function just looks like this. So we've got x going in this direction here, but what we're also doing is looking at time moving forwards. So as we move time forwards, we can see that, well, we already know what happens. If we increase time, we increase the variance, and that means that this function is spreading out quite nicely. Now, the reason this comes up in physics all the time is because lots of things in physics tend to spread out over time. You have things that are concentrated and they want to spread out. One of the most important things to a physicist would be heat. And so we can think about this sort of thing as being a temperature profile. We've got a particular material, we've got temperature that's focused at a particular point, but over time, we would expect that the temperature spreads out in precisely this way here. And so the Gaussian distribution comes up a lot when you're trying to model heat distribution or other things that spread out in the same way that heat does. Now, to make this mathematical, we introduce the so-called heat equation. So the heat equation is a differential equation. In fact, it's a partial differential equation. We discussed partial differential equations barely at all. The reason we decided not really to treat partial differential equations is because they're harder. The reason they're harder is because they're equations that involve differentiating a function with more than one variable in all of its different variables. But I think it's important to note here, because if we think about that probability distribution function we had before, so if we think of f as being, let me just look at my notes here. If we let f be equal to 1 divided by root 2 pi t times the exponential of minus a half x squared divided by t, then this multivariate function here actually satisfies this partial differential equation here. Because this solution seems to model how heat spreads out, and it happens to solve this equation here, we call this equation the heat equation. This is a very important equation that comes up not just in physics, but in probability as well, primarily because of the connections with probability theory between the Gaussian and heat that I've just outlined. But yes, this is the equation in mathematics, I would say. It models so much, it has so many interesting properties, and it just comes up all the time. So that's the heat equation. Now let's talk about another situation in which the normal distribution comes up. This situation is Brownian motion, which is probably a bit more relevant for those of you who like probability theory. So the setting of Brownian motion is as follows. Well, there is a correct definition of Brownian motion. I'm going to hint at that definition, but I'm not going to give you the exact definition. I just merely want to point out properties of the Brownian motion that come up in relation to the Gaussian distribution. So let's say that we've got a particle P traveling according to Brownian motion, whatever that means. Remember, I'm not actually defining what that means. So we've got a particle traveling in R, traveling according to Brownian motion, and it's traveling with speed equals 1. Speed in this context is also something that I'm not really going to explain to you, because with Brownian motion, things can basically move arbitrarily fast or arbitrarily slowly. But speed, when I say speed is equal to 1, this is just some sort of normalization. Essentially, I don't want my particle, even though my particle can travel arbitrarily fast, I don't want it to be traveling arbitrarily fast, arbitrarily often. So I need to somehow slow down my particle. And so I do that by setting the speed equal to 1, even though I haven't really defined what speed means either. So now you're thinking, well, what's the point of bringing up all these terms? Well, let's suppose we're going to start moving towards explaining the relationship between Brownian motion and the normal distribution. Let's suppose that the initial position of the particle is at this point mu in R. So it's at this point I'm strongly hinting at where the normal distribution comes in. I'm thinking about this as the expectation of x, where x is some normally distributed random variable. What is this random variable? Well, it's precisely the location of this particle after some time t. So we've got a particle that starts at mu. We're going to let it evolve for some time t. So, and then we're going to consider the random variable x, or x sub t, just to emphasize that it does depend on our choice of time. So this random variable is basically just where this particle ends up at time t. Now, it's a random variable. It's impossible to say exactly where it's going to be, but it turns out that because, well, by definition almost, since this particle is moving according to Brownian motion, then this random variable has a normal distribution, and the parameters that describe this normal distribution are mu, the location that it started off at, as well as t, the amount of time which has passed. Now, I want to spend some time explaining why this is such a natural thing, and I'm going to do that by imagining that t is small and that t is large. So if t is small, I've got a normal distribution which is centered at mu, but because t is small, that means the variance is quite small. So that means that, you know, it's got a lot of data, it's got a lot of mass centered around mu. And of course, this makes complete sense, because if the particle starts at mu, and we don't really let it travel for too long, then it can't really get too far. Or it can, but it's much more likely to stay close to mu. And the interesting thing is that it is possible that it went really, really far, because, you know, this probability density function is positive. There is a chance that it ended up all the way out here, but that chance is quite small, basically because of how the normal distribution operates. On the other hand, if we say that t is large, then the distribution should be much more spread out. And this makes a lot of sense as well, because if we're allowing the particle to move for a very, very long time, then really it could be anywhere. I mean, I guess there's a slightly bigger chance that it's stuck around the middle, but since we're allowing it to evolve for such a long time, it really could end up anywhere. So this is Brownian motion. as I said, I haven't, this is not the definition of Brownian motion, but it is quite close. You need a few more sophisticated tools from probability theory to completely describe how Brownian motion behaves. So yes, that's that. I'd like to, do you have any questions or comments you'd like to make at this point? I'll just pause for a brief amount of time. All right, if there are no comments, then I'll just point out to you that this actually brings my time with you as your lecturer to a close. So I've got one more slide. Thanks very much for having me as your lecturer this semester. It's been a good experience for me. You might be aware that I'm not actually not really a data scientist, but it's been a good experience for me to learn about this field, and hopefully you've had some good experiences learning about this as well. And I hope that you find that the content that we discussed this semester does actually come in handy. I thought to give this a final activity as a wrap up, I wanted to point out something that I found on the internet, which I found humorous and interesting. It was this particular meme here. So I can appreciate that you might think that this is not a very tasteful joke. So we've got Elmo here choosing between something healthy and something which is unhealthy. And the author of this particular meme is suggesting that mathematics, data structures, and algorithms are the healthy thing, whereas AI and machine learning is the unhealthy thing. So what goes to my mind when I see this is that I guess the author of this meme is thinking that maths is good for you, whereas AI is not. What about AI and machine learning would make this person write that? Well, they might get the impression that AI is an exciting field, but ultimately not very substantial. It's cliche. There's lots of buzz. AI and machine learning are basically buzzwords. They're quite popular, but it may be the case that people only do it because they think it looks cool. Now, while there may be some truth to that, it's not a very good place to leave this lecture. So I thought I'd point out to you that I do think that this meme is wrong. Maybe a correct way to do this would be to say that what's unhealthy for you is studying AI and machine learning without having first studied mathematics. So maybe that's the lesson we can take from this, because artificial intelligence and machine learning are certainly important fields, but maybe the correct way to approach artificial intelligence and machine learning is with proper training in the core sort of mathematics, the mathematics that we've actually been dealing with this semester. So yes, I'd like to leave it there. Hopefully what we've covered this semester does actually give you a solid foundation to treat these more advanced topics in data science. So I'll leave it there. Thanks very much for your attention. I hope that your quiz goes well for you in the exam week, and I certainly hope that things work out for you as you progress through your careers in data science. I'll leave it there. Thanks very much. I expect maybe we'll have a 10-minute break before Yoni continues to talk about gradient descent and neural networks.
Thanks a lot, Tim. Yeah, so we'll continue in 10 minutes. Yeah, that was a great overview of the normal distribution. And Tim, Tim is a pure mathematician, an expert of analysis. Would it be correct to say geometric analysis or partial differential equations.
I guess geometric analysis is the intersection of geometry and partial differential equations.
Yes. So yeah, that was very good. And yeah, what's happening these days is that pure mathematicians like Tim are contributing to data science, and sometimes vice versa as well. So that was great. We'll meet in 10 minutes in around hour Australia time. Okay, let's take a break. And we'll go for 50 minutes. So we'll have a 1 hour session, not a 2 hour session. With the exception of if there are questions about homework 3, assignment 3, I'll do them, and then maybe we'll extend the session just a bit more. But yeah, so maybe we'll start with questions about assignment 3 after the break, if you have any. Okay. Hi, MATH7501. Let's start with some questions about the homework. If you have further questions before we do this one last session. Does anybody have a question? Feel free to speak out or write it in the chat. Okay, so Kai has a question about 4B. Let's see. I think I've met a lot of you today during Data 7001, but it feels like we haven't met forever in Math 7501 because we haven't. And let's see. So question 4B. Okay, so the thing is that we'll actually, the focus of the lecture will be this kind of thing. First, in a more complicated context of deep neural networks, and then going back to the basics and looking at this. So is there, Kai, do you have a specific question associated with 4B? Or wait till we present things a bit? Oh, yeah. Determine the range of values. Use a gradient the same. About make sure. So where do you see determine the range of values? Hold on, I'm kind of, yes, 4B, first sentence, numerically or analytically? Return a question assignment 1. Do this numerically using gradient descent. That's numerically. Make sure learning grade step size small enough. Illustrate, this is a numerical section 4B. So about 4B, it's a numerical section where it's just suggested to you that eta will be small enough so convergence will work. I hope that helps. Tell me if not. Now there's a question for 4A, and it says, I try to use total table random distribution for one item on the sign, but the results far away from one with the number of item increases. I don't see 4A is not about that. So what is your question about 4A? Oh, 2A. Okay, 2A, sorry. Okay, sorry, my chat window is very, I'm not in Zoom teaching shape. Let's see, 2A. So, so Wenhouse says, I try to use the total of the table of random normal distribution 2, 3, 100. By the way, when you deal with a normal distribution in software, you have to make sure to check if the second parameter is the variance or the standard deviation. I believe that in Mathematica it's the standard deviation. So if we do question mark on normal distribution, yeah, the second parameter is a standard deviation. Okay, so sometimes people would put the second parameter the variance. Yeah, okay, I'll get back to the last question in a second. So then we have 2A. Wenhouse says, you did total of table of random of normal distribution 2, 3, 100, 100, but the result is far away from 1 as the number of item increases, for sure. Okay, so you're supposed to do a Riemann sum here. That's what you're asked to do. Okay. So approximating the integral via discretization is not summing up a random number of entries, or not summing up random variables. When you speak about a random variable, there is the random entity, which is an entity which is random and is described by the probability law associated with this probability density function. So what you're supposed to do is to take the density at a discrete fine grid multiplied by deltas. You would have had an example of that from Emina in the practical. I hope that helps one. Okay, now question from Anthony. Does it mean we have a program Mathematica to do gradient descent? Yes, yeah, but we're actually going to do this now in the next hour as well. Okay, hopefully with success. I haven't tried it before, so let's see. Okay, and Kai says helps with the Riemann sum. Okay, is everybody satisfied with the answers to the questions? Any? I don't understand what you're saying. Why other terms? Maybe Kai is asking why more than 100. Well, if 100 it gets numerically close to 1, that's good, but you can try more. Right. Okay. So it might be that by 100 it's already. It's not 1. It's just Mathematica is displaying 1 for you, not with full numerical accuracy. So you can do n pi of 30 digits. Here is pi to 30 digits. Okay. So, and if it's in 50 decimal precision, okay. So if we would have misjudged this and with 100 terms, what delta do you use? Oh, well, that comes from the 100. Yeah. Right. And right. So it might be that here, that for this question by 100, you're already very close to a probability density. Okay. That's okay. So there is no need to do the 1,000 or 10,000. Do them, but show the answer that it's already close to 1. All right. More comments, questions about the homework, or we move on? Okay. Okay, that's another comment on that. All right, 6:05, let's start. And you're here with me now for the final hour, where what I want to speak about and show you is a bit of deep learning, just a taste of, and hopefully you'll be convinced that with the notation, terms, linear algebra, even the discrete math, and certainly the calculus that you learned in this course. And these are the tools needed for deep learning. This is not going to be a full course in deep learning. It's just going to be a taster. And hopefully we'll get to do something similar to this question as well. I must say, I haven't tried what we want to do in Mathematica beyond the first try. I kind of find it exciting, so you'll have to help me if I fumble. Let's see. So deep learning, machine learning. One can speak forever about machine learning. Some of you have had a taste of this in Data 7001. Some of you know about it from elsewhere. Some of you want to be data scientists because of the excitement of machine learning. In the world of supervised learning, as most of you know, the story is that you have a variable x and a variable y, and you want to predict x in terms of y. Sorry, you want to predict y in terms of x, and this is called supervised learning. And you train a classifier to do that. So you collect data that has been pre-trained that I'll show you in a second. Let's just look at some data right as I speak. So this here is the MNIST data. You look at the first entry of this test data, or let's call it train data. And it is a image. This is an image, what you have here on the left of the digit 0, and it's labeled as 0. So on the left, you have the x, and on the right, you have the y. Okay, so I'll just do arrow x to y. And there are plenty of applications for this, for classification, both automatic systems that we want to create, but also, in a sense, more static data science, where we want to be able to classify customers based on their behaviors, based on their type. The sky's the limit. Okay, let's look at another data point. So here's another image of a 0. Let's go to, like, you know, here's a digit of 5, an image of 5, and it's classified as 5. Okay, So this data set, you've seen it before, probably elsewhere. Who's seen MNIST, the MNIST digit data set previously? MNIST digit data set. I forgot even if we looked at it in data 7001. I'm quite sure we did. I know not everybody's doing data 7001, but okay. So that's MNIST data set, and these three. This is how you get it in Mathematica. Now, I must say, Mathematica is not your archetypical data science software tool, and it's not your great machine learning tool, but it's a powerful tool. And we're actually just going to use the built-in machine learning framework or deep learning framework in Mathematica for a bit, just to train a neural network. The reason we used Mathematica for this course, even though it's unfortunately not a open source platform, is obviously because of its analytic capabilities. So you see a companion next to the, you're doing integration and differentiation and things of these sorts. And these things are in a sense algorithmic, so you do it with symbolic software like Mathematica. But now we'll use it for deep learning, just a bit. So this line here, it pulls the MNIST data set, and this calls the training data. And if we look at length of training data, it will be 60,000, and there's test data, which will have a length of 10,000. And there's a nice question: when we use built-in algorithms, how should we be convinced it's implemented correctly? We're never fully convinced, right? I mean, there are unit tests, there are sanity checks. Sometimes the code is open source. Deep learning algorithms that we're going to see now are anyway extremely noisy. But so how are we convinced? There is some aspect of trust as well. But yeah, I mean, that's true. Don't know what more to say about that. Okay, so a neural network, a deep neural network, is going to be a function that knows how to take such images, such as S5, or maybe let's look at a different one. Let's look at this one, or this 9. Okay. And would ideally look at the 9 on the left and know that it's a character 9, right? The character 9 comes from one of 10 labels. You know, you've got a 0, and you've got a 1, etc. This training data is actually sorted, so I kind of know that there is about 6,000 observations per digit. So if I go to like the 15,000 one, it's already at 2, and if I go to the 22,000 one, it's already a 3, etc. Okay. When you train, you'd often shuffle it, especially if you're doing a split, but that's not so critical here. And what we're going to do now is we're going to give you the complete box. Now, I just pulled this off the Wolfram website, and this is a complicated object. Let's unpack it a bit. It's something called NetChain. It has all kinds of specifications. We'll see what they say in a second. We won't get into every detail. And this is what you call a convolutional neural network. Okay. And it's a special structure of a convolutional neural network. This is called a LeNet. It's a neural network that was popularized in the late 1990s. Okay, so here we specify this model. Okay, now what is a neural network? It's a function that's going to take this image on the left and give us a number between 0 to 9 on the right. Okay, images on the left. Does anybody know how many pixels the MNIST dataset has? I can remember. So 16. So it's a good guess. It looks kind of like that, but they're 28 by 28. Okay. So there's 28 by 28, and 28 by 28, if I remember correctly, is 784. There's 784 pixels on there. So each pixel has a specific intensity. Let's actually look at that for a second. Let's just do something a bit more. Let's call this X. Just this training data sample. And I think that if we do image data of X, I think that this function, oh no. So this thing has two things. So let's take the first thing of X, the first of X. I think that would work. So this would extract the image. Let's call this xim, that x image. And look, if I look now at the, I can do a matrix plot of xim. It's a 28 by 28 matrix. Okay, so if, for example, let's look at some pixel. Let's look at the pixel. Let's look at this one. Let's look at xim, the 3,7th pixel. It's actually just a value 1. I think that's kind of fully dark. But if we go to like this one, let's go to 10,20. Let's go to 10,20. And it is some value that's closer to 0. So the 1 here is completely dark and the 0 is completely light. Of course, so what you do with this, so what you do with this encoding, you can flip it, etc. I mean, you can, these are numbers between 0 and 1, and it's kind of arbitrary what's light and what's dark. Okay, so in this sense, the data is a matrix. But if we'd like, we can also, let's take this xim, let's take this image, right? So this is this matrix, here it is. That's this matrix, okay. Matrix, oh, we could have also shown, what is it called? Matrix form, right? Here it is as a matrix, okay. Here we actually see it as a matrix. Okay, here it is. I mean, you can actually see the image. This is this matrix, okay. But let's not worry about that too much. Let's do join of xim. I think that would work, and flatten. And this is what you'd call the vectorizer matrix function typically. So let's call it xmv. They're like xim vector. So this should be a vector of 784. Of length 784. Okay, so often when we work with images, we actually just vectorize and take row by row, or maybe it'll be column by column. It depends. It doesn't matter so much. Okay, in this case, it was row by row when we did because mathematical matrices are nested lists, and it's a 784 dimensional vector. Of course, you know, this is not as it's not as instructive to plot it here. I'm doing some basic things, but just so of course, you know, we could do a list plot of xim. You know, here it is. It doesn't tell us too many things. Sorry, xmv. Okay, so this is a plot of the index of the vector and the value. Okay, does anybody know why there are no points here? Can anybody have a bit of an indication why there are no points here and no points here in this plot? So again, we took this image and we vectorized it. So this is these are up to these are the this should be the dark areas above here. Yeah, so this is this dark areas above the 3 and below the 3 here, and that's what you see there. But that's not so important. Yeah, the margin, exactly. That's the best explanation. The margin. Good. So we know now what's these are what our x's are. Okay. And in deep learning and machine learning, you almost always just treat your data as some sort of vector. And now we get back to this very complicated object, which I didn't explain what it is yet, and I won't up to a detail. I'll only give an overview. And what a deep learning model is, it's a function that you can then apply to this vector, okay, to this 784 dimensional vector. That's what it is. It's a function that you can apply to this vector. This function gives you, I think, gives you in this case, a predicted label. Now, what we're going to do is we're going to use this built-in function, which is called nettrain. It's kind of cool that this is built in. And nettrain trains a model. So it's going to train this function Linnet. Now, this function is parameterized by a bunch of parameters on the training data. As we train it, it's going to check all the time the accuracy on the test data, because the data is split between the 60,000 training data and the 10,000 test data. Okay, that's what it's going to do. And it's going to do what we call 3 training runs. Let's just run it. And whoa, this inbuilt thing is kind of cool. And what do we see here? So what it's doing is it's breaking up the data into batches, mini batches, and that's a common thing that you do when you train a deep learning model. So you're learning the parameters of a deep learning model. There's a question, is the number in the vector the grayscale? Yes, the number in the vector is a grayscale, between 0 and 1. Okay, and what we're doing is we're getting some sort of objective which all the time compares how, we'll see the loss function in a second, it all the time compares how we're doing to what we'd like to do. And it's also actually, this is a bit chopped here, it says error rate here on the left. It's also computing the error rate. It's all the time checking the value of the function you have and checking it on the test set. And we're seeing that it's getting to below 2%. So that means that about 98 out of 100 digits that it sees at the moment are classified correctly. Okay, we could stop this. We don't need to let this run all the way. We could stop this. Now the fan on my computer, by the way, has started kind of going. Okay, I stopped it. And if I now look at this Lynette, so it had undergone some training. So the parameters of the model are now trained to a level, okay? And they are in some arbitrary, initially random parameters, which are, by the way, typically initialized from a normal distribution, the same normal distribution Tim spoke to you about at length, okay? So this is a model. And let's now try and apply it on, let's take some 30 images. Here are 30 images, and apply it on these 30 images. So it actually applied on this first image, it said it's a 1. On the second image, it said it's a 2. On this third image, it said it's a 5, etc. So it seems to kind of work. I mean, out of 100 images, there'll only be about 2 that aren't correctly classified. I mean, it should work well. So it's quite likely that out of this 30, they're all classified correctly. And that was the act of training a deep learning model. At this point, one can take all this information that's here, and it's quite a lot of information, okay, and export it and use it in a production model or anything of that sort. Okay, so now let's get into a bit of details. We have 2 main things we want to do, and then we do want to tie it, and all in quite short time, we do want to tie it to this thing, which, by the way, is also a deep learning model right here. It's just a very degenerate deep learning model. It's not so deep. It's of depth 1, and it's without a nonlinear activation function. So least squares linear regression is your kind of degenerate deep learning model. All right. So the first thing, what I'm going to do is I'm going to open notes here from, this is something that I'm working on with the colleagues. This is actually notes in progress. I mean, we could use, we could get this from many places, but might as well use it here because we've been working on this now. There's so many resources for deep learning, and you'll do this much more beyond a course of mathematics basics, which is a course you did. The resources you see here are related to, if you go to this website of Benoit Lequin, Charles Mock, and myself, Deep Learning Math, you'll see some information here, but it's in so many other places. And you guys are busy now. It's the last week of semester, so it's not time to look at other things, not before you've done all the assessments you need to do in the preparation, things like that. Okay, so a deep learning model, you probably saw illustrations like this before. Okay, so you take inputs, x1, x2, x3, x4. Okay, in our case, we have up to x784. And schematically, you pass them through layers, maybe one layer or maybe many layers. Okay, maybe which are hidden layers, and then you get some output. In the case of our type of model that does 10-digit classification, you don't get a single output, a single scalar output, but you get an output of 10. And these are the probabilities, the estimated probabilities of being in a digit 0, digit 1, digit 2, digit 3, up to digit 10, up to digit 9, sorry. Okay, so that's schematically what a deep neural network is. And you call each one of these circles a neuron. That's what they're roughly called. But let's look at it mathematically. It's actually mathematically very simple. So, and we call this a feed forward because it moves forward, as opposed to a convolutional network, which is also feed forward, but is not. And what we trained here was actually a convolutional network, but it's in this Linnet thing. It's a convolutional network. This is, you see convolutional layers, but it's in a sense, it's a specialization of the more simple model that I'll speak about now. Okay, it's a specialization which reduces the number of parameters and uses the fact that pixels that are neighboring are related. Okay, so sometimes when you look at the data set, you know, each different feature or each different variable is completely kind of not related to its neighboring variable, so you can do any shuffle. But here in image data and voice data and things like that, it's obvious that one needs to consider locality. So that's the story of convolutional neural networks. We won't speak about that further. All right, so the goal is to have some function f star from Rp to Rq. What were again P and Q for our case? Just to see we're on the same page. What's P and what's Q in our example? So what are the dimensions P and Q in this digit example? We take in an image and we give, so yeah, P is 28 by 28, which is 784, and Q, the output of the network, gives us 10. Okay, it gives us 10 probabilities, and then the way the classifier works is it chooses the maximal probability. Okay, so in our case, P is 784 and Q is 10. And you know, there is some unknown function f star. I mean, that function is in me and you and you and you and you, and that's that function that actually knows how to look at digits and see what they are. But what we're going to do is we're going to have some approximate function, which we call f sub theta, which is also from Rp to Rq, and it does this. Now, in deep neural networks, what you do is you do function composition, and we studied about function compositions. I mean, there's not much to it. Okay, it's function composition, and you compose the function f theta out of this first function and the second function and the third function, and each one is going to be a layer. Okay, so deep when you have many compositions. Okay, although even if depth is 2, you already call it deep. Okay, so the Lth layer is from dimension NL-1 to dimension NL. Okay, so see, dimension is how many neurons you have per layer. Okay, and the choice of the type of model is part of the quote unquote art of deep learning. Okay, there's not an immediate recipe of what to use, but sometimes you do some experimentation, you see what works and what's not. So what would be these dimensions? Okay. And the depth is the number of layers. So the first layer is of dimension P, and the last layer is dimension Q. Okay, so the number of neurons is just the sum of these things. Okay, now this is kind of the key thing, and let's see that we understand this. Okay, so just look at this schematic here. So the value of an output neuron at each layer, and you call this like the L minus first layer, okay, then goes through the process of becoming the value of the neuron at the Lth layer. And there's two parts to it. One is an affine transformation. The word affine transformation, that means multiplication by a matrix and addition of a vector. Okay, so you have some matrix here in addition to the vector. Okay, so this matrix multiplication is what you see here, all these arcs between the previous layer and the next layer, that's a matrix multiplication. The addition of the vector in machine learning, we call this sometimes a bias term. So this is this intermediate variable, which we call Z, which is the, after you've done just an affine transformation. But then you apply a nonlinear activation, which is to Z, which gives you the actual value of the neuron. Typical nonlinear activations include the sigmoid function or other functions that just kind of allow to incorporate some nonlinearity. So you see, this is what you have in this layer. So if you now put this thing together with this function composition, then if you want to look at a simple neural network, what it is, you can write it as follows. You can say, I'm going to have some function x. Okay, this is a neural network with two layers. Some function, sorry, f, that gets an input x. I'm going to apply to it matrix multiplication plus vector addition. I mean, that operation, we could say loosely that operation is linear. I hope you guys do the course MATH7502. You'll learn what linear means really and things of that sort. But you know, it's linear plus a term, so it's really affine. Fine. So you do something that's not so exciting, but then you apply this nonlinear operation to it. Okay, so this was the first layer. Then you take this input again, you cascade it into the second layer function. So you again apply a nonlinear operation. Okay. Yeah, this is a mistake. This W2 should be on the left-hand side. Okay. Plus this other function, and you apply that again. Okay, that's all a deep neural network is. And if you had more layers, sure, you get more. You get something like that. Okay, that's what a deep neural network is. The parameters the network learns are these matrices W and the bias vectors B. That's what you do in the action of training. So when we ran such a thing in Mathematica, let me run this nice thing again. Let's do this net train thing again. It's just so impressive that you just run it and it runs. Okay. It's now already, sorry, it's already trained from before. So it's kind of already in a good performance. So you don't see the things going down. But when you run such a thing, what's happening is it's trying to calibrate these parameters of the W and the B, and the W and the B. And if you have a deep network, you have many W's and many B's. Again, what we have here is a convolutional neural network. So the matrix W, even if it's 1,000 by 1,000 matrix, it's not going to have a million parameters because it often has repetitive parameters. It uses things called convolutions, which you'll probably learn about in a different course. Okay. All right. So why is this good? Well, it just turns out that you can express, and there are rigorous theorems for this with rigorous mathematics, you can almost any function you can express in an arbitrarily close manner with a neural network that already has depth of 2. Okay, so by having just this combination of something that's both affine and some nonlinearity, and affine and some nonlinearity, you can already take any arbitrary function and get an approximation for it, which if you get more and more, if you increase the dimension of these W's, that means if you get more and more of these neurons here, you know, they go more and more and more, if you get more information in the network, then your approximation will become closer and closer. Okay, so, and these are types of things that are formulated in the machine learning and artificial intelligence literature as theorems. Okay, we won't look at such a theorem per se, but the point is that you can get arbitrarily close in precision. Yeah, so you need limits and things of that sort, just the same type of stuff you guys have been doing. All right, so now we're left with the question of how to train such a thing. Okay, how to train such a thing. And for this, let's just go and I'll go to the, I'll share now the screen here. So let's share my writing tool. And let's just speak about training parameters. And let's see. Okay. So training f theta. That's our function f theta. And by training f theta, we mean learning of theta. So in this theta, in the case of neural networks, had this W1 and the 2 and the B1 and the B2 are all these parameters. Okay, so it's not some arbitrary function. It was a function with a very specific form. So typically when you train things, what you're going to do is you're going to look for a loss. Now, I'll put this in the context of your homework 3. Okay, a loss might be something of the form sum I1 to n on all sum on all observations of f theta xi minus yi squared. Okay, it's not necessarily the loss we use for a classification problem like this neural network that we've seen, but that's the loss I'd want to speak about, and that's your basic loss function. Okay, that's the least squares loss. Well, sorry, it's called the L2 loss or whatever. Okay, so you have data points. You have data points x1, y1, x2, y2, up to xn, up to xn, yn. Okay, looks familiar. Starts to kind of look like your homework, right? You have these data points. In the context of deep learning and machine learning, etc., these x's here are going to be high dimensional. Okay, so again, in our case, each one of those x's was an element of R784. Okay, that's oh, that went somehow up there. I don't know why. Funny, look, I can write here. Write an A. It adds an A. Let it be. Let's not play with. Okay, let's move on. All right. So, and the y's were digits. Okay. But in general, if you now go a second to your question 4 of the assignment, then each one of these x's is just a scalar, and each one of those y's is also just a scalar, right? Now, let's for a second reduce the this f of theta from the complicated, deep, advanced neural network to what you have in the homework. So in the homework, f of theta was, you see that I'm using the same notation that you have. It is f theta of x, of any x, is beta 0 plus beta 1 x. So your theta is just the tuple beta 0, beta 1. Okay, that's your parameter. Your parameters are just beta 0, beta 1. That's your parameter. Okay, so of course, if we rewrite this objective, let's just write it. So then you've got sum I1 to n of beta 0 plus beta 1 xi minus yi squared. Okay. Now, what's the idea with this objective? If this f of theta was really super, super close to the actual thing, then for any x that we put, it's going to give us exactly y. And then this will equal that. And the difference is going to be 0. And the sum of 0 squared is still 0, so your loss is going to be 0. However, as this thing deviates from yi, you pay a penalty. Okay. Of course, this is greater or equal to 0 because it's sum of squares. Okay. Now, this loss, we can just write it as L of beta 0, beta 1. And if you don't mind, I'll just put here a subscript x, comma y, and I'll put like vector xy. This is like the data. You see it kind of changed. In your function that you were estimating, the subscript, the thing that was a parameter was your learned parameters. And now for a loss, your data is fixed. Your data is a fixed thing. Okay, because the data is fixed. We sampled our data. We have our x's and our y's. Okay. You can plot this loss. You can plot this loss if you'd like. And if you were to plot it, and we'll do it in a second for an example, well, I'm not sure we'll do it for that, but I'll just give you an indication on how to plot it. You know, you'll actually see that if this is a beta 0 axis and beta 1 axis, and this is the loss axis, then there is some point here. Let's call it beta 1 star, beta 2 star, which will be the global minimum in this case. Okay, so what you're going to get is a sort of an upward facing parabola. In this case, it's a quadratic form. It's something you'll learn about more in MATH7502. So in general, and you can show in this case that, you know, this actually has a unique minimum and this function's even convex. It's nicely behaved in this case. In the story of more complicated and more advanced and often more useful, even though this is useful also, deep learning models, it won't be just this perfect, beautiful quadratic form that goes up, and it won't have just a unique local minimum. So here there's a unique local minimum. I'm talking about local minimum in 2 dimensions in this case. Okay, and it'll be more complicated. Of course, in a deep neural model, then, you know, you won't just have 2 parameters, beta 1. So the dimension of theta is not just going to be, it's not just going to be an element of R2, you know, it's often going to be an element of R a million. Okay, so you often have about 1 million parameters, or 10 million, sometimes even about 10 million, or 100 million, or 10 million. Okay, or even a billion. I don't think that a trillion, maybe, in very big models. So you have so many parameters, okay? So of course you can't plot this. But the theory still holds, or the principle, and that's kind of nice. Okay, so how do we optimize this? There's a whole field of numerical optimization. We even have a course. I even know, I think that Kai, at least Kai, you've taken this course last year. We have a student that put the, so MATH7501. So I recommend, by the way, so, okay, let's do it a bit of an ad here. So next semester, you've got MATH7502. If somebody actually found that this course and you kind of know a whole lot of math, you might want to go to MATH3204 instead. So this is numerical optimization and numerical linear algebra and optimization, MATH3204. Okay, you can do this course. Okay. So there's a whole world of optimization. Fred Rooster, yeah. So Fred Rooster is, okay. And Kai says it's tough, but Kai didn't do MATH7501 prior, nor MATH7502. And Kai's a tough guy anyway, I think. But anyway, you passed it. Good. All right. And even more. All right. So that's MATH3204. In that course, you learn about actually a whole bunch of very advanced optimization techniques that don't do just the basic thing I'm going to show you now. And let me show you the following thing now. Beta 1 t plus 1. And I think you've seen this also previously, but that's okay. Okay, but you just see it again. Beta 0 t, beta 1 t minus eta times the gradient of the loss at beta 0 t, beta, this is around bracket, beta 1 t. Okay. So I spoke about MATH3204 for a second. MATH3204, you do other techniques that are second order techniques and more advanced, etc. Okay. But these techniques are often not superb for very high dimensional models, you know, with 10 to the 9th parameters and non-convexity and things like this. So we stick to this technique. What's this technique called? What's this recursion called? What did I just write here? So I wrote here a recursion for if you start with some beta 0, 0, beta 1, 0, okay. You start with some vector, beta. What is this thing called? Somebody. Gradient descent, that's what it is. Okay, so you start with beta 0, 0 and beta 1, 0, and then you go for t equaling 1, or you could even go for 0, 1, 2, etc. You follow this recursion, so every time you take the value and you subtract eta, which is a constant, a non-negative constant, okay? multiplied by the gradient. So you go in the direction which is exactly opposed to the direction of steepest ascent. So then you descend. I mean, this loss function is designed to be minimized. If you were maximizing for some reason, you'd put here a plus. Okay. All right. So you do that, and you evaluate every time the gradient at your previous point. Okay, so if instead of plotting it this way, we would plot now, I'll just take here, let's call this the beta 0 axis and the beta 1 axis. Okay, these are your two parameters in this case. You might start in some point, let me just call this point beta 0. Okay, so by beta 0, I mean the vector beta. Okay, here. Okay, and then you took a step in the direction which happened to be the gradient at that point. So you took that point and computed the gradient at that point. Okay, and the direction, the magnitude was also determined by eta. Okay, by this eta, and you got to this second point, which is beta 1. Okay, and then maybe the gradient changed a bit and you went here, and that was now this point beta 2. And maybe the gradient here changed and you got, sorry, this straight line, and you got to this point, and that's beta 3. And you continue. And hopefully after a while, the differences between beta t and beta t plus 1 will diminish, and you would stop. And you continue, and you stop. And if you stop, and if this thing works, okay, it's not guaranteed to work, but if it works, then maybe here I'll draw contours of this thing, although the contours I'm drawing here are not agreeing with the gradient, because the contours should have been like this for the gradients to be, okay? Okay, so maybe this function is very weird like that. Okay, so you end up at a stable point at a local minimum. Of course, for this to work, you need that eta won't be too big. Okay, and in some clean models, you can actually compute analytically what is a good eta, but otherwise you need experimentation. Because if eta is too big, then you take these big steps and you actually never stop at the right point. Okay, so in this deep learning framework, all that is done is gradient descent. And what a deep learning framework does for you and does well, and we won't see the details, we just don't have time, is it computes gradients. It computes gradients. So there's something called the backpropagation algorithm, which is an algorithm of something called automatic differentiation, which takes this nested model and reapplies the multivariate chain rule in a smart way again and again and again. Not such a complicated way that we could in another 2 hours and study it. Okay, and it computes gradients for you. All right. Now, in the case of our example, you can actually compute an expression for the gradient analytically, right? You can do that. Now, instead of solving this for you, the homework, and I know that Amina also did something like that in the practical, let's take it one step beyond, okay? One step beyond, I see it's 6:46, so we'll finish in 14 minutes, okay, in the round hour. Okay, let's try and do something and finish in the round hour. So instead of having this type of model, this f, which was very simple, let me take it just a slightly more complicated f, okay? What I'm going to do is I'll do f theta of x is ax, okay? It's a matrix ax. In our case, the matrix A is sometimes called the design matrix. We'll just have ones, ones, one. Oh, sorry, f theta. I made a mistake. F theta of x is ax. No, that's not what I wanted. Sorry. Oh, sorry. That's not what I wanted at all. So what I want with f theta of x, let me just write it as f theta of x as beta transposed x. Okay, we'll do that. All right. And then, okay, we need another step or two for that. You can actually take a matrix A and you'll put here a column of ones, and you'll put here x1, x2, x3, etc. up to xn. Okay, instead of beta x, sorry, I'm just doing this on the fly. So let's do it. Let's call it. Okay. Forget the f theta of x. So just do a beta 0, beta 1 transposed times 1x, first of all. I mean, that's just writing this as a matrix. Okay. As an inner product. Okay, that's the same thing we've had here. This is beta 0, this is this thing. All right. So that's beta 0 times 1 plus beta 1 times x. And then you can take a matrix A, which you would call your design matrix. And I'll just copy the objective here so you have it, right? So I'm going to just copy this objective here. So I'll write L beta 0, beta 1, which before we wrote a sum I 1 to n of beta 0 plus beta 1 x minus y xi yi squared. And I'm going to write it as a x minus, no, mistake, a beta minus y norm squared. Okay. To see this state, you'll need to take another minute later on. So if you multiply, if you take, I'll write it in a different color here. If you take a beta 0, beta 1, and you multiply it by this, and you have all the beta 0 multiply that, all the beta or beta 1 multiplies that, and then you're when you're doing the norm squared, well, you're each time taking this estimated value, subtracting it from the y. This is a whole vector y here, yeah. And this is a two-dimensional vector beta, and this is the same matrix A, okay? And norm squared, that just means a beta minus y transposed times a beta minus y. Okay, so what I want to say is that you can write the loss this way. That's actually not critical for our point. Now, it's actually also not hard to see, and we won't do this now, but treat it as an exercise perhaps. Okay, and you can do it element-wise if you'd want, and then get to it. You can actually see that the gradient of this beta, okay, let me now just treat it as a vector beta, okay? Beta is again beta 0, beta 1, okay? And you can see that the gradient is going to be an expression which is 2 times this matrix A transposed times the matrix A times beta minus y. Okay. So this is something you would need to calculate offline and see. The matrix A transpose, you know what that is. The matrix A, you know what that is. Y is the vector y. Okay, and the matrix A has the x's in it. Okay, so this thing has both the x's and the y. Okay, now we like this. We like this because then if we're doing gradient descent, and this, by the way, it's true not just for simple linear regression, just with 2 betas. It's also true if we have 784 betas, or if we were to do that for digits that we're looking at. Okay, so if we now plug this in gradient descent, then you can say that beta t plus 1. I'm now treating beta as a vector beta. Is beta t minus 2 eta, I've just put the eta here before the 2, that's not a big deal, times A transposed A beta t minus y. Okay. Minus y. And this is how you would do a gradient descent recursion. The thing is, we have 8 minutes, and let's take it as a challenge. I haven't done this before. I need your help. Let's take it as a challenge to do this thing in mathematical. Let's try to do this in mathematical. Okay. And to do it for what? So the nice thing is that we don't have to only have this simple thing that you have in the homework with just, you know, a vector of 1s and then the x's. You can actually have 784 different x's. So you have 784 different columns. So our matrix A would be 1, and then it'll have x1, x1, x1. Now I mean by this one something else. This is like the first feature, and then it'll have an x2, 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 x2. This is the second feature, up to x784, x784. So each image is going to be, this is like the vector of the first image, and this is a vector of the second image, and this is a vector of the third image, etc. Okay. Now there's a question, in practice, is a gradient normalized? No. No, so in practice it's not. What does happen in practice is that this eta, this rate here, which is sometimes called the learning rate, is adaptive, and you have a different eta for different coordinates. Okay, so here you have 2 coordinates, but maybe you have 1,000,000 coordinates. Line search is not so common these days. So the common algorithm in deep learning, at least, that has become the norm is called ADAM, which is a combination, it's adaptive gradient descent with momentum, which is really, as I just said, it's gradient descent with something called momentum. Okay, so let's go and do something in Mathematica. Let's do it. Any questions? Any more questions? I hope you're finding this a bit useful. All right, so what are we going to do? So let's, you know what, sorry, we'll leave the digit classification and we'll go back to a simple thing. Okay, so let's just take our x data to be 1, 2, 3, 4, 5. Okay, and our y data to be, and I'm just going to make up data 1.1, 1.9, 3.3, 4.2, 5.7. Okay. All right, that's just the x and the y data. All right. So, and let's do gradient descent to find the line of best fit. Yeah. Now, I don't even need to plot this. You see that this is sort of like the straight line, 1, 1.1, 2, 1.9, etc. Okay. I guess I could do a list plot of x data versus y data. I hope this will work. That didn't work. How do I do a list plot of? Oh, no, I forgot list plot. Does anybody know on the fly? List plot of okay, life's annoying. So we do x data, comma y data, and then I think if we do a transpose of that, and it will do this, and transpose, and I think if we do a list plot of that will work. Cool. Okay, so you see here's the data, almost a straight line. Let's see that we can actually figure out that it's a straight line. Okay, just the chat window has run away from me. Here it is back. Chat away. Okay, so what we want to do is we want to have this matrix A. Okay, A is a design matrix. So the matrix A, and let's just say n is the length of the x data. Okay. So the matrix A needs to be of the form. It needs a how do you make a ones in Mathematica? Do you fill? Is there a fill? No. There's range. There's I don't know because so I'll just do it. Repeat. Forgot repeat. No. How do you do a ones? So I'll just do a table of 1, comma, I'll do it like this manual. I do a table of 1, comma, x data I, for I going 1 to n. Okay, and if I look at this as a matrix, is this what we want? Yeah, this is our design matrix. Okay, good. So that's going to be our design matrix. Okay. And now let's make our gradient function. So let's do grad, which is a function at some beta. Okay. This is how you define a function in Mathematica, right? And what was it supposed to do? And we have some learning rate eta. Okay, we have some learning rate eta. So we'll do, oh, but that's not part of the gradient. So the expression we had for the gradient was 2 times A. I actually have it here. It's 2 times A transposed. So 2 times transpose of A. Now matrix multiplication, if you remember in Mathematica, you do a dot, times the matrix A times beta minus the Y. And the Y is our Y data. Okay. Will this work? I hope it will. Let's see. So let's see the gradient at the point. Let's put at the point 1, 1. So 1, 1 is like the beta. So we get some vector which is potentially the gradient. With, well, if we got it correctly, it's a gradient. Okay. Or let's look at the gradient at the point 10, 1. Okay, this would be the gradient. Gradient is a vector. Okay. Let's look at the gradient at some other point. Here it is. Okay. All right. So with this gradient, now if we want to do the gradient descent, it's not hard. What we want to do is we just want to have our beta 0. And let's start at some point. Okay. So let's just start at the point 100, 100. Okay. Of course, starting, initializing gradient descent when you do this simple thing that we're doing now or doing deep learning is a thing of its own. But again, when your learning rate is small enough and you have enough patience and the problem is nice, this thing will work. And we should find the best beta, which will be the line of best fit that would go through these points. Okay, we'll even plot it maybe. Okay. Oh, we're supposed to finish? Okay, give me 5 more minutes, 3 more minutes, okay? I hope this is useful also for your homework. All right, so if you do grad of beta 0, then here's a gradient at that point, okay? So then beta 1 is just going to be beta 0 minus eta times this gradient, right? And let's define an eta here, and let's define it numerically to be, I don't know, 0.0001. Okay. So let's see both beta 0 and beta 1. Oh, we didn't run this row, this cell. Okay, so we moved a bit. We moved a bit. And similarly, of course, I'm not going to type this forever, but let's just do one more. Beta 2 is going to be beta 1 minus eta, the gradient in beta 1. And, you know, there was a bit of movement. Now, of course, if my learning rate would have been bigger, if my eta would have been, say, this, okay, and I'd run this. So now, look, we moved from 100 to 99 in a bit. Let's run these 3 steps. Of course, we moved, and by the way, we moved like far out. I think this was too much of an aggressive learning rate, okay? So, you know, let's go back to this one maybe, and it seems like we're doing some sort of steps. Okay, so what do we do now? I don't know, let's do a for loop. Do you remember how to do a for loop? I don't remember how to do a for loop. So for starts, so for, let's write the start as like this. For beta 0, I'll copy this, is some initial condition, comma, the test, okay, let's do the test of the norm, okay, so how do we stop? So one way to stop is if you have the, let's look at the norm of the grad of beta, of, let's say beta 0. It happens that when you get closer and closer to the local minimum, then the norm of the gradient goes to 0. Okay, so at the local minimum, the gradient is 0. Sorry, the gradient is not 0, but the norm of the gradient is, yeah. I mean, at the local minimum, the gradient is the norm at the local minimum is 0. So so if we just do and let's not call this beta 0, let's call this beta, and then we do here the norm of the gradient. Let's do test. Let's do that as long as the norm is greater. You see, it repeats until test fails. Okay, so as long as a gradient is greater than 0.1, for example. Okay, this is all. And the increment, let's not do anything. So let's just leave it empty. And the body, let's do this main step. Okay, which is going to be beta equals beta minus eta grad beta. Who knows if this will work? And let's also do, let's do two things in the body. Let's do this, and let's do print norm of beta. Or let's just do print beta. So I'm hoping this will work. Let's see. This, I mean, for loops are a bit funny in Mathematica. That's okay. I mean, not like funny, haha, just like funny a bit. Okay. Let's see, for, run this. Oh, it does something. It does something. And it even seemed to have finished. Okay. Did it? No. I mean, that's, see, we never know what the parameters. So what I've done is I've now, so I'll do that. I've killed my output now, right? With this printing. That was a big mistake to do all this printing. So sometimes when something runs on a computer, no big deal. But if you actually fill your printing, then that's it. The computer is now a bit tired. So, but I think it survived. So let's just do this without the printing. And run it again. And it runs. And let's look at beta. Okay, so this is beta. All right. What's the slope of beta? 1.11. So, and I think we found the right beta, right? Because, or we found a beta. So if you would plot this beta, look, it's a beta that has, if I do a plot of beta, the first one, plus beta, the second one. So this first one is this intercept, and this is the second one is what we call beta 1 before, times x for x going from 0 to 5. It's this line that goes straight up. I'm not overlaying this plot and this plot, but you can do that. That's all gradient descent is. And I know this looks very simple, but just contrast this with this complex thing that ran here. It's kind of the same thing, only with much more complexity and more details, which you'll need another course or two to understand, but not so much. Okay, I spoke all over the place. This will be also in GitHub. Are there questions? No? No questions. How to prevent overshoot? There's not a golden silver bullet for that. So to prevent overshoot. So class question is how to prevent overshoot. So Kai realizes that if we take an eta which is very, very small, this thing will run very slow, and if we take an eta that's too big, there'll be an overshoot. But that's why you have other methods which make eta a bit more adaptive, like Adam, but still they don't work perfectly. Gradient descent from an optimization perspective is a very primitive algorithm, but it turned out that for this thing of learning the parameters for deep neural networks, it's pretty much what we have today. Okay, because you're just doing steps. Your gradient is in 500 million dimensional space sometimes. So you're computing a gradient vector which is in 500 million dimensional space. So you have to do that effectively, and that's what you do with algorithms called a backpropagation algorithm. Okay, so there's just a question about 3a. We'll get to that in a second. Any more questions about this this final demo of your course? No? Okay. So there's a question about 3a. Let's see. 3a. Okay, right. So this 3 is I like this 3. So yeah. So the nice thing about this 3 is this is gradient descent, but in one dimension. Okay. So it's not hard to show, and it's kind of nice that the mean of the points is the thing that minimizes this. Okay, you can see it in different ways, but you're doing here gradient descent in one dimension. So, but what you're getting is effectively a sequence. You have a sequence of xt, and you can compute the gradient. Obviously, this is just quadratic, just like you can compute it here. Okay, and the gradient is just going to be the derivative with respect to u of this loss. Okay, so compute it, massage this expression, and get it into such a form. When you see something like this, it typically looks like something that came out of a geometric series, or a finite geometric sum. Okay, so that's a hint for that. All right. Okay, and Kai is helping as well. More questions, thoughts? All right, so together with Tim, I wish everybody a good end to the semester. You still have the practical with Amina this Friday, and that will prepare you for the third quiz, which is in the form of a final exam, and we'll give a bit more information about that third exam setting, etc. No hints for the final exam, but we'll send some information. So again, the final exam is pedagogically is like the third quiz, but it's a bit more. Okay. And yeah, there will be a formula sheet for that exam. All right. So if that's it, let's finish and bye everybody. Thank you. There's just a question from somebody that wants to ask me about data 7001. So I'll go to a breakout room for that. And thanks a lot. Thank you. All right. So what I'm doing is I'm doing a breakout room. If somebody wants to see me for a second, 7001. So just go to room 1, or just say in the chat if you want to go to this room, and we'll speak for a second about data 7001. I'm stopping the recording. Bye, everybody. Bye-bye.